Yeah, can you please get back to that page, that portion?
Sure.
Yeah. So, ma'am, I mean,
I'm saying that a map.
No, ma'am, that's okay. That's okay. I had a clarification. Maybe I had a question. I mean, for the second chart, D psi, we can see that it's smooth on U intersection V, but D psi need not to be smooth on the whole V. No? I mean, is it like that? Okay.
Yeah, that is fine, right? But we are not shaming. We are just shaming it to be smooth at the point psi P.
Okay. I mean, it's smooth at the intersection. That's fine.
Yeah. So
Okay.
yeah. So all we want is that the composition is smooth at the point psi of P.
Yes.
So whenever I take a composition of F composite psi inverse or F composite psi inverse,
Okay.
then that composite map should be smooth at the corresponding point in the Euclidean. And that is happening.
Okay. Okay. Yeah.
Hello.
Yeah.
Ma'am, can ever be U intersection be empty?
No, see, if U intersection V is empty, then we have nothing to worry about.
Exactly.
Yeah.
But U intersection we can't be empty because
See, P, because if it is containing P, right, V also contains P, right? And U also contains P. Then at least P
Okay.
is there in the intersection.
Okay.
So,
Thank you.
yeah. Okay. So now let us
हेलो
move on to the
भाजी
more
कल फोटो
interesting
देखे
part.
गए थे कि फैमिली पिक का
So again, I will
शाम ਨੂੰ
discuss it first point wise. Then we will go to
ਉਹ
Euclidean
ਫੈमिਲੀ ਦੀ
FOB
ਸੀਗੀ
or global smoothness if it is
ਸ਼ੀਸ਼ੇ
smoother than
ਵਿਦਆਊਟ
FOB.
ਸ਼ੀਸ਼ੇ
And
ਸੀਗੀ
that strategy we all understand. So
ਹਾਂ
so again, we don't have any
10
license
12
to
ਦਾ
talk about smoothness if I restrict to M and N, but we have to somehow
हाँ
take
जी
and this map and drag it to some Euclidean domain, right?
नंबर तो ਇੱਥੇ ਲਿਖਿਆ ਨਹੀਂ ਹੈ
Euclidean domain and analyze smoothness there. So I will say F is
ਨਹੀਂ
smooth
ਕਿਹੜਾ ਨੰਬਰ ਕਹਿ ਰਹੇ ਹੋ ਤੁਸੀਂ
again for some P which is a point in M.
अच्छा 9988 मोबाइल नंबर
That is fine. So maybe I will first draw
हाँ
the picture. So
ठीक
what
है
I did, if I had on one side Euclidean space, then I will just compose what I did last time. I just composed F with psi inverse, and that map took us to a Euclidean domain, and there we could analyze the smoothness because of the existing calculus. So here on both sides I have some non-Euclidean, possibly non-Euclidean setup. So what I will do, I will consider a chart containing P. I'll call that U comma psi.
हाँ जी
Then I have FP.
हेलो
This is my M.
हाँ जी भाजी कल फोटो देके गए थे फैमिली फोटो
Different
10 12 दी
and this is my N.
आओ
So
बन
this
गई
is also this is also n manifold. So this M is n
ठीक
dimensional, N is n dimensional. So I will get a chart around FP as well with a manifold n. Maybe this is how the chart gives us. Okay. And now I can choose, if necessary, I can choose U slightly smaller so that F maps U to V. See, why can I do that? Because if I have one U and one homeomorphism phi from U to some Euclidean open set, then if I choose a smaller open set and restrict phi to that open set, it will still be a homeomorphism onto its image, right, by usual topological arguments. So I will choose U suitably so that f of U is contained in this coordinate chart containing f of p inside the codomain space n. Okay. So now what I do for
Madam,
the
is there
description
any
of,
relation
yeah,
between M and N, small m and small n?
no, I'm just writing they can be completely independent of each other.
Actually, M is a n manifold. N is n manifold. That's why I am
Yeah,
telling.
yeah. So I was just writing this n use in the beginning, so I don't want to change the dimension n.
Now,
Okay, that's
actually,
why.
dimension of is m. Right hand side is m.
Yes.
Is there any relation between small n and small m?
No, no, it's just a notation. That's all. There is no. You can change the name also. This n can be just called some m prime. That's fine.
Now, are
There is
they
no
of same
connection.
dimension? Are they of same dimension?
That's what I'm saying. There is no relation. There can be any number n at m. Natural numbers.
Okay, they may be different dimension, m and n.
Exactly.
Of
They
okay.
can be different, same, anything. Yes. Okay. All right. So now let us go to the
Ma'am,
next. Yeah.
to make sure that f of u is contained in V,
Mm-hmm.
uh, because as you said that we can restrict on a smaller set u, smaller
Yes.
subset of u, so that the
Yes.
image lies in V. Don't we
Smaller
need the
open subset.
yeah, smaller open, yeah, open. I specifically want to mention. Don't we need the
Mm-hmm.
continuity of f also for that? Because what you are basically
Yes.
doing, you are taking f
Yes.
inverse of V, and you are
Mm-hmm.
taking the intersection with u, and
Mm-hmm.
that is basically the subset of u you are taking to make sure the
No,
image
no.
lies in the
There is nothing about continuity. See, my I have chosen an open set U from M and
yeah.
open subset V from L. And suppose my FU is not contained in V, right?
Okay. Hmm.
So there will be some intersection, right? FU will intersect V because both contains the point F of U.
Right.
Okay. So I will choose my U sufficiently small so that F of U is smaller than this. Okay. So of course, as you what you are saying, I understand, but we don't need continuity to get this. Okay.
And how you can you guarantee that there will be a smaller open subset of u, say u prime, such that f of u prime is contained in fu intersection v?
How can I guarantee that?
Yeah.
Uh, if not, then I can just take the intersection.
Intersection of what?
F of U intersection with V.
Uh, no, basically we want a subset of m, right? But f of u intersection v
Right.
is subset of n.
Right. Right. Oh, okay. You are saying how do I get a smaller? So I how
Subset
do
of
I
u.
get the yeah subset of U which will be mapped, right?
Yeah, that what you said,
Okay.
right? That if fu is not contained in v, you will find a smaller
Right.
subset of u.
Right.
But we can take F inverse of the intersection V
But
and then
to
take a
make
small
sure
step.
f inverse of v is open, we have to make assume the
No.
continuity.
I mean, we can take just take F inverse U F inverse V intersection U, and then we can take a smaller subset containing V which is also inside because of
But
conformality and all
no,
of
no,
that.
no. Why it will be open?
Hmm. Let me think
Uh,
a little bit.
U to Rn is a homeomorphism, right?
Yes. Yes.
So we can take a ball in Rn which contains the image of P and take the inverse. That will be a open set, right? A smaller open set.
That's
Yes.
okay.
Yes.
But ultimately, we want f of u should be contained in v also.
So what he's saying is that F of U should be contained in V. That how do I guarantee?
Yeah.
Okay.
Yeah, one way I can see is you take basically u tilde you want, right? So you can
Right.
take f inverse of v and take it intersection with the u.
Right.
And to make sure that is open,
Mm-hmm.
must have the continuity of f so that f inverse of v is also open.
Yeah, maybe you're right. So I will think about it. So yeah, we can assume that F to be continuous because anyway these are topological spaces, so that means that is fine. Right. So if I assume this to be continuous, then yeah, F inverse V will be open, and
Then you can take intersection with the U.
yes, correct, correct. Then I can take the intersection. Yes. So apparently it seems that the continuity is needed, but I'm still not completely dismissing that. Okay, if I don't assume continuity in advance, then we won't be able to get smoothly. Maybe I will think and tell you in the next session. Yes. So yeah, if so, let us assume a priori that F is also continuous and say that it is continuous. Okay, so we will always be able to find, so that's what we are assuming, that a chart u comma phi, this will be mapped to the chart v comma psi on the codomain, right? And then still we are not doing anything that can help us because we are still not in the Euclidean setup. So we are first going to the Euclidean Rn, Euclidean space Rn, and here I will go to Euclidean space Rn, right? This will be the image of u under phi, and this will be the image of v under psi, right? So this is my map phi, this is my homomorphism psi, and here I have a map like this. Just compose it. And this map is P inverse followed by F followed by psi, right? So this will take me from this open set of Rn to this open set of, sorry, I have drawn it wrongly. Yeah. Yeah. So to this open set of R of Rm. And this map, I know what it needs to say, that it is smooth at phi of v, right? So if this map is smooth at phi of v, I say that F is smooth at v. Okay. So let me just write this. If there exists a coordinate chart u comma phi containing p, or rather not there exists for any coordinate chart, and containing fp such that f of u is contained in v, we have is smooth at phi of v. And now again, there is nothing special about these charts, u phi and u psi, the manifolds m and n, right? We can choose different charts, and since they are all compatible, so what will happen? Suppose I choose u1 u1 again containing v. This will show the independence of this definition of chart. Okay, suppose u1 psi1 here containing fp satisfying similar properties, right? Then what will happen? I will have psi1 composed with f composed with psi1. But again, if I restrict it to some suitable open set, I will see that this will be same as, how do I change my this map to the earlier map? So this will be psi inverse. This I know is a smooth map. Then psi composed with f composed with psi inverse. Again, this I know to be a smooth map. Of course, we have suitable substrates, but they are all open substrates. Therefore, this composition, I will get for this composition also at the point phi. This actually tells me that there is okay. And now if I vary my point, I will say that F is smooth, just like the previous case, if it is smooth at all points. Any questions at this point? I'm still audible, right?
Yes, ma'am, you are audible. There are no questions.
Okay.
So in the definition, we are not saying that F is continuous, right?
Exactly.
Hello?
Yes.
Hello?
Yes. We are not saying it.
Okay, okay.
Can you look at the diagram?
Yes, yes, ma'am, yes.
The first map, when we define, we just took any map. Say that F is continuous at P. From what I just said, first go to the continuous state. So I'm saying that F is smooth at P. Okay? That means F composes phi inverse at phi of P. Can you say something about the continuity of F at P of smoothness? Because what I can recall from this map, this is going to be an open set. This is going to be an open set, right? So the continuity should follow from here. So I'm saying that F composed with P inverse is smooth at from this. So this is a Euclidean smoothness, right? So this means that this is also continuous.
Yes, yes, yes.
Is everybody following me? Then what I can do, I can write
Yes,
F
yes.
as F composition phi inverse composed with phi. And this is a continuous map. So is the second one. So F automatically becomes continuous. Right? Smoothness implies continuity.
Ma'am, but in the second definition between the two manifolds,
Yes.
they still are taking continuity in the definition of the smoothness.
Have right now I'm this is a good question, but yeah, I will give you the answer.
Yeah, in the first one, it's clear that the smooth map is continuous automatically in the first case.
Yes.
For the
Yes.
second case, we are pursuing this.
Yes. Yeah, I think yeah, what can we do? Yeah, maybe I will the four quantum chart. Okay, F of U contains okay. There does not exist any this open subset of M. Therefore, F of U is contained in U. So I will suppose that this is a continuity. And for that, we don't need a continuity argument.
Agama?
This can be a way out. Yeah, this can be a way out, but the thing is still how we will make sure that our definition is independent of the coordinate charts.
Hello,
No, that's what we are saying. One
hello,
coordinate chart was
Atrey, hello. I think, hello,
hello, hello. Am I not audible?
yes. I am just saying that your first case, which you have taken, smooth map on a manifold, actually that is a particular case of that is a particular case of a manifold. Hello. I am just saying that the first case, that first case, hello, hello.
Yes, yes.
I am just saying that the case you have
Hello.
taken in A means first case, actually that is a particular case of second one. Means smooth maps on a manifold. That is
Yes.
actually a particular case of smooth map between two manifolds.
Yeah.
Actually, this n is we can take there in first case and Rn as a manifold. And where you are using
Yes.
continuity, I think that here just participants are also saying that we should take as to be a continuous map between these two manifolds, because first case is just a particular case of this one, and there we are saying that that is continuous. So
Sorry.
no, no, but all these rules are being obtained from the Euclidean function, and in Euclidean we know that the function is smooth or it is differentiable where it is continuous. Otherwise, we can't do this.
मैंने रखे
So
No, no.
I think that
कूलर से बोल
here f must be continuous.
कृष्णा फर्स्ट अफवाह जो है वो ये है कि आपको लेडीज कपड़े पहनने की इतनी आदत हो गई है कि रात को कश्मीरा की मैक्स पहनते सोते हैं। ये भगवान बात है रात को पहन के सोते मैं तो दिन को भी कृष्णा फर्स्ट अफवाह जो है
Okay, fine. Fine to be safe. And we have realized that this coordinate chart for this composition is a smooth map, right? This is really smooth map. And now similarly we will prove that its inverse is also a smooth map in the sense of manifold. Okay. So that way what we have actually proved is that phi from U to phi U is not only a smooth map but it is a diffeomorphism. So what do I mean by diffeomorphism? I haven't defined it yet. So a map, a smooth map is said to be a diffeomorphism if it is bijective. This is the smooth inverse. So maybe this will be my definition part C. So I'm just defining it before giving the example. So part C for that. C says that X from M to N, where M is a diffeomorphism F is smooth, maybe a bijective smooth inverse. Yeah. So is this definition clear? An example, please. Guys, I don't see any feedback. I'll go back to it again. Is that fine? Yeah.
Okay, ma'am, we got it.
Hello, ma'am. Your voice is cracking.
Okay, actually I have a bad signal today, so I don't think, yeah. If anyone thinks I'm not audible, please stop, try to extract again. Okay?
Okay.
Yeah. So now let us go back to, am I audible clearly now at least?
Yes, yes, yes. Yes, yes. Please go ahead.
Okay. Okay, fine. So now let us see some more examples. Suppose, so I consider, so we saw some projection maps, right? So which we defined in the context of the projective space. What was the projection map? We took, so what was the projective space? Real projective space consisted of all straight lines in Rn plus 1 passing through the origin. And what was the projection map? So we just took a non-zero n-th space, Euclidean n1, n plus 1 space, which was say x1, which was x1, x2, xn plus 1, and we called it x. And we mapped it to the equivalence class, where x and y are supposed to be equivalent if they lie on the same line. That means if they differ by a scalar multiplicity. Okay, it is equal to lambda times y for some non-zero real number, right? So we want to prove that this is a smooth map. The projection is a smooth map. Okay, so now let us, so this domain is a very easy example. It is, we have a Euclidean open set. So I will just choose any chart I have to choose, right? I have to define it point wise and in terms of chart. So what I will do, my atlas for the manifold, domain manifold will be just the single one. The entire space for this entire Euclidean space. That we can do in any open set of Euclidean space. So remember, we had an atlas for RCS then into that was from 1 to n plus 1. And what was ui? Ui was all those points are being n which are coordinate non-zero. And what was the map pi? It was ui to rn. And how was it defined? We just send this equivalence class consisting of x to the point x1 just by crossing the xi. So xi minus 1, xi plus 1, and then xi. So I got a point in the Rn, right? So that was very similar to the spherical chart what we saw yesterday. Okay. So now the charts on both sides are quite clear. And so what we have to find out is we have to pick some point in the real projective space. And suppose it belongs to the real projective space and this projection map is surjective. So it must be coming from x, which has one of the rn coordinates non-zero. If all the coordinates are zero, then it must be a zero vector in the Euclidean n plus 1 space, which is not possible, right? So then there exists some ui such that of this sort, such that x will belong to that particular Euclidean n, right? So that I can be variable, but there will be such an open set that we have chosen. Okay, so this is what happens. So I have
गर्मी होगी ना दोबारा से बारिश होने के बाद भी गर्मी फिर होएगी मौसम भी
yeah. So what I will do is I will change my atlas on the
रीड हट जाओ
domain.
आज तो किसी के घर गए किसी के नहीं गए क्यों अरे एक तो दूसरा हो गया दूसरा
Such that
मैं देख रही हूँ ना देखा नहीं वाला सभी अच्छा हो ही खराब लग रही है मेरी ना मेरे
an open set of rn plus 1 minus
मेरे को मन ही नहीं किया ये देखिए बड़े वाला पेपर दे दो छोटे वाले ले जाओ बड़े वाले पे इसके क्वेश्चन आंसर
slightly more, slightly bigger atlas. It could be for sure, but this certainly contains this atlas that we saw. And so the maximal atlas containing both this one and the
टेबल के
previous
नीचे
one
लगा दिया सोनी
is the same that I realized.
नीचे ऐसे लगा दो नीचे से आगे से लगा दिया
Structure given by this atlas. So now we have to find one open set or one coordinate chart from rn plus 1 minus 0 such that pi maps that open set to U. Just how we define this entire smoothness. Okay. So define ui tilde to all those points x1 up to xn plus 1 in rn plus 1 minus 0 such that xi is non-zero. Actually, this is an open set of rn plus 1 and also rn plus 1 minus 0. Okay. So now pi of ui is actually equal to 0. So now we have this diagram. We have this punctured Euclidean space rn plus 1 only the origin is taken away. I have this which is now so I will just write it like that. So here I have this open set ui. I have this open set tilde, such that UA tilde is not right, but the map pi. What was the corresponding map here? It is the same. Go to Rn plus pi. Yes, so it will be the identical map. What is the corresponding chart here?
रिमोट तो दूसरे दिन से चल रहेगा रिमोट होना चल रहेगा
This is my chart. I equal to Rn. Yes. Transpose. What is that I? It is actually the entire Rn, not a particular open set, because there is no variation on other coordinates x1, xi minus 1, xi plus 1 up to xn plus 1. All real numbers are associated. Xi was chosen to be non-zero, but that has been dropped. So this n tuple will be actually the full Rn. So I will just erase that. Yes, full Rn. And now I have to prove that what is the corresponding map? I compose this line, compose this. I will prove this first. I will do that itself. So I can say this pi. I have to prove that this pi is right. I can prove this. I can just look at this diagram. It will be this diagram. This psi I, pi. So this side on the diagram is example. This I have to prove that just what is the map? Starts from Euclidean open set I tilde, where this is xi, x1 up to xn plus 1, and maps this point to x1 up to xi minus 1, xi plus 1, and then, so it just drops one coordinate. Very much a smooth map. In fact, it is a linear map. With the setup of smooth manifold, we have proved that this x actually is arbitrary, and this is a smooth map at all points. Alright? So is this proof clear, everyone? We have chosen that, we have chosen the last
I have a confusion here. Phi I will be, I mean, last time we defined this phi I to be x1 divided by that 1, 0 coordinate, right? Divided each of these coordinate with
oh, that's not
otherwise it will not hold, right?
Yeah, you are absolutely right. What I will do is, this will remain the same thing.
Ultimately it will work out.
Yeah. This is definitely a smooth map. It is each component is transpose. Yeah, thanks for pointing out. I was actually confused. another acute manifold now, M, another acute manifold M, and there is a fused mass from N to M. And I want to define something like the total derivative at each point from this point. In case M and N both are Rn, both are M and Rn equivalent, derivative is another is a linear mass Rn to Rn again. S is a mass from Rn to Rn. Open subset of Rn from N to M. Total derivative again a function from Rn to Rn itself. But what is interesting, in the beginning we use Rn as a topological space where its elsewhere point. But in the second description of derivative, this is a linear mass. This is a mass from the vector space Rn to Rn. Properties of Rn is so I have to linear space dependent on M space is called the tangent space. This is the what is tangent space? It is a space consisting of tangent vectors. Now what is a tangent vector? I think you have already seen tangent for tangent plane for smooth surface. Right? That's how it looks, I guess. If I just have a curve, parameter will be moving point on the plane of free space, then the corresponding perpendicular. Velocity vector is represented by arrow that matches something that is happening at all points. Similarly, if I have to find out, I consider the North Pole. I want to find out its tangent space at the North Pole. See this that is touching the sphere at this point. So all these or it should not be a curve or how do I make sense of tangent space or tangent vector? So tangent vector will also be like this, that touches the smooth curve or smooth surface at that point. For that we need to revisit the notion of tangent vectors in R. First understand the vector. We will define that just points out the direction of the again, take can be also treated as a vector, right? They have comma and the so we have okay. Each point has an position vector, right? It can be represented by an arrow, arrowhead, the vector of position, and the comma when we talk about vectors, this is a very common form where what we call the semantics of position. So base point. So suppose I have a vector that is coming from the origin, that is also fine. And suppose I choose a point P, then translate the same vector to the origin.
मेरे यहाँ से
It will be the same vector. It is easy.
नहीं नहीं, मेरा तो माइक और वो म्यूट ही है।
Doesn't mean
नहीं नहीं, मेरे एंड पे मेरा माइक म्यूट है सर। ये किरणदीप मैडम है कोई, ये कोई और है? ये अभी मैं फोन पे बोल रहा हूँ, आपको आवाज आ रही है? हाँ, मेरे एंड पे तो मेरा तो माइक म्यूट है। आ रही है आपको आवाज मेरी? मुझे तो नहीं आ सर, मेरी आवाज तो नहीं आ रही क्योंकि मेरा तो माइक ही म्यूट है। मेरा म्यूट है सर, मेरा तो म्यूट है। ये आरती भट्टाचार्य का चल रहा है अभी, और अभी बीच में किसी का ऑन हो जाता होगा, लेकिन अगर वो देखना पड़ेगा, मतलब इसमें कितने हैं आप? 112 बंदे हैं। अगर मैं तो अभी लैपटॉप के पास ही बैठ के बात कर रहा हूँ, तो ये भी आवाज आनी चाहिए आपको, ठीक है? तो मेरी आवाज तो सर नहीं है उसमें, या फिर जो मैम बोल रहे होंगे, आरती मैम, उनके बैकग्राउंड में कोई आवाज कर रहा होगा। बट अभी तो हम बोल रहे हैं इतनी जोर से, अभी आवाज नहीं आ रही। ठीक है, कोई बात नहीं, आप मुझे बता देना वैसे भी। ठीक है, ठीक है।
And there is a canonical isomorphism with the differences origin this will be called then this will be called the geometric tangency is also verified, F times P is there. So everything is there, and even infinite dimension is there. That's fine. Now, how do I know which vector is actually joined to the map which defines the relation of vector map which acts on a function given
हाँ जी
function on Rn
नहीं ना
gives me a real number.
ना
Precisely something that we already said. The directional derivative
that
of f is the direction of g at the point.
हेलो
This is precisely what I'm trying to do. This is
जी
point,
अच्छा अब देखिए
right? Because b is a vector that starts from
नहीं वो एक्चुअली मैंने सिस्टम की आवाज़ बंद कर दी अभी उस सिस्टम की आवाज़ अगर हो सकता है मेरे हिसाब से होता नहीं है
of f, the directional
अभी देखिए
define linear. If I take
अभी ठीक है
linear say this lambda 1 lambda 2 then lambda 1 lambda 2 linear combination is split into
अभी भी आ रही
the
है ऐसा तो नहीं
corresponding directional derivatives and their linear combination.
नहीं नहीं बच्चे तो नहीं बोल रहे
This is certainly a linear number.
ये मैम के बैकग्राउंड में तो नहीं आ रही जैसे जो बंदा बोलता होता है ना सर
Can be
तो उसके माइक से आवाज आती है
linear map or linear functional defined on the vector space P infinity Rn.
गूगल मीट पे आवाज नहीं आ रही
First observation.
अच्छा
Second observation is that there is a product rule of derivatives, right? This product rule or Leibniz rule says that if I
मैं देखिए ये मतलब यूट्यूब पे आवाज आ रही है ये कह रहे हैं आप
real valued function,
मैं चेक करता हूँ
first
देखता
the
हूँ सर
directional derivative of f while we evaluate g at t, which is a real number, and then I keep the evaluation of f
मतलब यूट्यूब पे आवाज आ रही है ये कह रहे हैं
the directional method.
मैं चेक करता हूँ
This is v at of g. So this is the product. Each geometric tangent vector satisfies this rule. Okay. And in particular, suppose I consider the vector
हेलो
such that x is a derivation at, and this we define to be the tangent space of Rn at. So this sounds a bit abstract and this sounds a bit unnecessary as well, because we already had a geometric visualizable version of tangent space. Just shift the Euclidean space to the point where you want to understand the tangent space. That gave you all information, and that was canonically isomorphic to Rn also. But it is difficult to find similar description for tangent spaces of smooth manifolds in that sense. So that's why this abstraction of tangent spaces is needed. But nevertheless, yeah, question? Yeah, but nevertheless, we can prove that this tangent space that we have just defined is nothing but an isomorphic copy of the geometric tangent space of Rn. Then we will be fine. So what does this mean? So this is my first proposition, say. So TPRn is canonically isomorphic to the geometric tangent space of Rn at P. Or in other words, we are saying that every derivation that is an abstract linear functional defined on C infinity Rn is the directional derivative or is some directional derivative for some tangent vector of Rn at P. Okay, so how do I prove this? So naturally, yeah, so I'm saying all this, but before that, is it at all clear that TPRn, that is the set of all derivations, is a vector space? So I have a collection of linear maps from C infinity Rn to Rn, which has this product rule. Okay. So if I consider the collection of all such derivations, is this easy to see that it is also a vector space? So if I consider linear combination, yeah, any
you have to
answer?
compute. Yeah, you have to compute this.
Yeah, we just have to compute. It will be a real vector. If I have lambda1 x1 plus lambda2 x2, and how does it act? See, the space of linear maps on between two vector spaces, they form a linear space. That is clear. So the moment I have two linear maps, I can add them. I can consider their scalar multiples and so on. So the linear combination of two linear maps is well defined. And how does it act on a smooth function f? So that is also well defined. This is x1f, and then this is lambda2 x2f.
Hello, ma'am.
Split like this.
Hello,
Yes.
ma'am. Here you say
Yeah.
every derivation is a directional derivative. Yes. And how
Yes.
here
Yes.
how we can define total derivative?
Yeah. That is we are coming there. So we are first trying to make sense of partial derivatives as
Okay.
some
Okay.
differential operator or differential operation on functions. Not differential, but linear maps on functions, right? So that we can do the same, we can take the same strategy to define the tangent space of a smooth manifold. We will define the total derivative only when we have a well-defined tangent space. Because for defining the total derivative, we need a tangent space, right? Is this clear?
Yes, ma'am. Yeah.
Yeah. Yeah. let me, since I started a bit late, so I will take 10 more minutes. Is that fine? Is that fine?
Yes, ma'am.
Hello?
Yes.
And there are 100
Professor.
participants. We all have to agree.
Yeah. Fine if I
Okay.
take 10 more minutes?
Some of
And
us
it's
have
fine
left,
for me.
but
Hello.
some of us have left. Ma'am, one question is there.
Okay.
Will you see the before slide? That
Yes.
is the where you have defined or you have written RNP, that is superscript N subscript F, a P is equal to within arrow bracket, second bracket PEI, P comma EI, I equal to 110. And what does it mean? It is a dot product or something like that. P comma EI. RNP. Yes.
Oh, no. I'm saying that this is the basis of
Basis.
Rn. This is a vector space of n-dimensional vector space. And what will be the canonical basis for this vector space? It is just the standard basis of Rn shifted to the point C.
Okay. Thank you, ma'am.
Spanning the notation.
Okay, ma'am.
Spans the entire vector.
Okay. One more questions that we have.
Let me quickly prove this.
You have defined a derivation P at P, that is C infinity Rn to R is a linear map. So you have defined on Rn. Later on, will you define on arbitrary manifold?
Yes.
Will you define?
Yes, that is the idea. Yes.
Okay, ma'am.
And
Okay, ma'am. Carry on.
Right. So we can first see that this tangent space that we have defined abstractly is actually a copy of Rn, the geometric tangent space at P, and hence by transitivity it is also isomorphic to Rn. Right? So then how do I see that? I first define a map which starts from the geometric tangent space at P and takes me to the set of derivations or the vector space of derivations. So I will consider any vector in the geometric tangent space which will be a vector emerging from P, and I just send it to the directional derivative at P with respect to the vector V. So this is the derivation. We already have observed this, that it actually is a linear map acting on real valued functions, and it also has the product.
It is a tangent space homomorphism as well. I mean, vector space homomorphism.
Yes, this will be a linear map. Yes. So first observation is that phi is linear. Why? Because if I take linear combination of VI, then I get a linear combination here as well, and that this is an easy check. So that I leave for you to check. This is linear is fine. The important thing is that it is an isomorphism. So I have to prove it is injective as well as surjective. So how do I do that? So all I have to prove is that its kernel is trivial. So it has only 0 vector. So basically, suppose I phi of some vector p comma v is 0. 0 as a derivation. That means when it acts on any function f, that gives you 0. So that is, this is 0. The directional derivative of f with respect to v is 0 at p for all functions f. Now, how can I write this p of v, right? So suppose I just consider p of v, then I can write it, because it is it can be written as a linear combination of basis vectors. So maybe I can consider this vi. So I'm just mimicking what I do for Euclidean space, but only keeping the base point as it is at P. Right? Is this clear? This can be written like this?
Yes,
Yes,
ma'am.
yes, yes.
Okay. So now I write this and acting on F as the. So similarly, what I can do, since so so the directional derivative of this, I know that this also is written as the, by definition this is nothing but right. This is by definition, and this is at P. And what is this? This is nothing but Vi times the standard Euclidean vectors Ei acting on F, the directional derivative Ei acting on F, and that we are saying is 0. Right? For all F. So in particular, if I choose F to be the following map, so I just choose any point x1 up to xn and send it to its jth coordinate. So this is a projection onto the jth coordinate and call it fj. Okay, so this is a smooth function. There is no problem with that. And what will be by my assumption, I have to have the directional derivative of fj with respect to v has to be 0 for all j. Now what will be the directional derivative of fj in this direction? So if I split it in this manner, what I have written here, it will be the directional, so the partial derivative del f del x I multiplied with vi. But the only partial derivative that survives is the jth partial derivative, that is 1, all others are 0. So what I am left with is bj, and that has to be 0. And that is true for all j. What does that mean? That means that the vector that we started with has all the coefficients 0, and so this has to be the 0 vector, right? So what is the 0 vector? This is p comma 0. Is this clear, everyone? How we got the 0 vector?
Yes, ma'am. Yes.
Yes, yes.
Great. So the injectivity is taken care of. Now the only thing is we have to prove that this is onto. So we just start with some derivation, abstract derivation, and we will just find out that there is a geometric tangent vector PV such that the corresponding directional derivative is equal to x. Okay. So now, how can I write x? Is there any? So I think I'm already quite over time. So maybe I will just stop here because I think I need 2-3 more minutes to finish this proof. So we will take this in the next session and start from there. Okay. So is there any question? So you also check this at home if you can finish the proof. I have already shared the lecture notes with you. The proof is done in detail there. So you see if you can go through it, and if there is any doubt, maybe we will take it up in the next session. Okay. We'll stop here.
Okay, thank you. Thank you, Dr. Say.
So,
Yeah. Sorry. Yeah.
so now,
Yeah, we're going over time.
yes, yes. Thank. So now, please join the tutorial session scheduled to be held from 4 p.m. Okay. Thank you all.
Yeah. Thank you very much, everyone, for your attention.